Okay, so today I will talk about why quantum computers cannot work. Maybe before I go ahead, I will explain one word in the title, which is the word why. So here, why does not refer to a mathematical proof. I don't expect a mathematical proof for why quantum computers cannot work. And it does not refer to a scientific proof, although this can be part of a scientific proof, but it refers, the answer to the word why is simply an explanation. So I'll offer an explanation for why quantum computers cannot work. And this explanation, I found it plausible. It's not just of theoretical interest. I think it's plausible and perhaps quite possibly correct, but to become a full proof, there is quite a lot of work to be done. So let me start by thanking again. This is the end. This is my last lecture in this semester, and this was a wonderful semester. And I would like to thank the Simons Institute and Dee Karp and Alistair Sinclair, who are running it, and Elchanan Mosel, who invited me to this special semester on real analysis and theory of computing, and also the Simons for making it all possible. Okay, quantum computers are hypothetical devices based on quantum physics that can outperform classical computers. A famous algorithm by Peter Shor shows that quantum computers can factor an integer n in c times log n cubed steps. The study of quantum computation and information is a remarkable interdisciplinary endeavor which involves several areas of physics, computer science, chemistry, engineering, and mathematics. The question if quantum computers are realistic is one of the most fascinating and clear-cut scientific problems of our time. And my work is geared toward a negative answer. The main concern from the start was that quantum systems are inherently noisy. We cannot accurately control them, and we cannot accurately describe them. To overcome this difficulty, a fascinating notion of quantum error correction and a remarkable theory of quantum fault tolerance were developed. The debate on quantum computers. What makes it still hard to believe that superior quantum computers can be built is that building universal quantum computers represent a completely new reality in terms of controlled and observed quantum evolutions, and also a new computational complexity reality. What makes it hard to believe that quantum computers cannot be built is that this may require profoundly new insights in the understanding of quantum mechanical systems, including in regimes where people do not expect such new insights. So it's hard to believe that quantum computers can be built, and it's hard to believe that quantum computers cannot be built, but it's even harder to believe that both these answers are correct. So we must find or indicate what is the correct answer. Why quantum computers cannot work? So here is my explanation for why fault tolerance quantum computers cannot be built. Quantum systems based on special purpose quantum devices are subject to noise which systematically depends on the quantum evolution of the systems. This dependence reflects the dependence of the quantum device on the dependence of the noise on the quantum device, and the dependence of the quantum device on the quantum evolution it is performing. Here, a quantum device refers both to human-made and to natural devices. This systematic dependence causes error rate for general-purpose quantum computers to scale up. The mathematical challenge is to understand the systematic laws for this dependence, of course, within the framework of quantum mechanics. So this is a one-slide explanation, and the talk will largely be elaborate this explanation. Debate. From the end of January 2012 until November 2012, Aram Harrow a brilliant researcher in quantum information and computation from the University of Washington, Seattle, and now he's at MIT, and I, were engaged in a public academic debate regarding this question. The debate was hosted on Dick Lipton and Ken Regan blog Gödel Lost Letter and P equal to NP. Further discussions with Peter Shor and Aram Harrow on smooth Lindman evolutions, which is a special a topic that will be discussed later, took place later on my blog. So here is the first post of this debate with Aram Harrow. The title that Ken and Dick gave it was Perpetual Motion of the 21st Century. And here it's how it started. Initially we thought that the debate will take only 2 posts and a few weeks, but then it went, and there were altogether 8 posts, more than 1,000 comments, and it spent almost a year. Okay, so here is how this lecture is going to be built. The first part will be on quantum computers. Then I will discuss noise, quantum fault tolerance, and the trivial flow. The third part is my conjectures. The fourth part, my conjectures are an attempt to formally distinguish the noise models, the noise behavior expected in the ordinary models, and what I expect them to be. The fourth part will zoom in on a smooth Lindman evolution, which is part of my overall picture. And then the fifth part will discuss a few conceptual issues for my debate with Aram Harrow. Then we will briefly discuss methods to avoid quantum fault tolerance, to show superior quantum computation without quantum fault tolerance. And I will talk about BKS, noise sensitivity, and boson sampling. And finally, we will summarize. Okay, so we reached part 1, quantum computers. So anytime you want a break, just say it, and anytime I want a break, I will say it.
Okay.
And also, if you have questions, it's possible you are the only audience, or you have some questions that other people you think might have asked, but it's not necessary. Okay, so we move to part 1, which is quantum computers. So what is a computer? We have n bits of memory. Each one can be in 2 states, 0 and 1. At every computer cycle, we can perform a gate on 1 or 2 bits. We need 3 types of gates, AND, OR, and NOT. So what is amazing is that these 3 types of gates allow any type of computation we witness around us, both in computers and in natural computation. And now we will try, based on this very, very simple model, to describe what is a quantum computer. Now, one intermediate step between classical computers and quantum computers are hypothetical devices that we can call probabilistic computers. Now, we don't have probabilistic computers, but we can think about them as devices where the states of the bits will not be 0 or 1, but will be some classical probability distribution, like with 1/3 probability 0 and with 2/3 probability 1. And then, starting with probabilistic bits, we can still apply these 3 gates, NOT, AND, and OR, and get complicated probability distribution on the entire state of the computer. This is in fact possible, and this is a very useful, one of the most fruitful, useful ideas in classical computations, pioneered by Michael Rabin and others. And it is the idea that randomization can give you advantage in doing computations for algorithmic purposes. The issue is that we don't need a device for that, because in classical computers, whenever we have a random bit, we can immediately sample it. So we don't have to maintain a probabilistic gadget. But as a thought device between classical and quantum computers, this can be quite useful. And now we jump right ahead to the world of quantum computers. So what is a qubit? A qubit is a piece of quantum memory. The state of a qubit can be described by a unit vector in a two-dimensional complex Hilbert space, H. We assume that a basis of H consists of two vectors, 0 and 1, with this very characteristic bracketing in quantum mechanics. So we have a two-dimensional complex Hilbert space. So the state of a qubit can have the form A times 0 plus B times 1. This is simply a linear combination where the absolute value of A square plus the absolute value of B square sum up to 1. So this is a qubit. So it is a single piece of information. It can be in infinitely many positions described by these two complex numbers. And a qubit can be measured. So essentially it's a 3-parameter space because you have here 4 real numbers but one relation among them. And a qubit can be measured. And this will give a probabilistic bit that we discussed a bit earlier, which is 0 with probability the absolute value of A square, and 1 with probability the absolute value of B square. And now, after we understand what is a single qubit, we can quickly jump to describe what is a quantum computer. In a quantum computer, the memory consists of n qubits. The state of the computer is the unit vector in the tensor product of all the two-dimensional Hilbert spaces corresponding to the qubits. And now we can perform gates on 1 or 2 qubits. There is a small list of gates needed for universal quantum computing. A gate is simply a unitary transformation acting on the corresponding 2 or 4-dimensional Hilbert space. And it acts like the identity on all the other parts of our computer, just similarly to the model we described for classical computers. So the state of the entire computer is a unit vector space in this huge 2 to the n-dimensional Hilbert space. And this state can be measured. And this gives a probability distribution on 0, 1 vectors of length n. Okay, we move to the second part, which is noise, quantum fault tolerance, and the trivial flow. So do you think I should change the position of this picture in each part cyclically, or this looks not bad?
I think it's good. Here
This
it
is
doesn't get in the way of the text that often.
Yeah, I think this is quite good. Okay, so we will continue with this. Concerns about noise. So the main concern regarding quantum computer feasibility is that quantum systems are inherently noisy. This concern was put forward in the mid-90s by Landauer, Unruh, and others. We can think about noise modeling, error modeling, and risk modeling as different notions for the same thing. For quantum systems, leak of information amounts to noise, and this is often referred to as decoherence. The early concerns that quantum systems are inherently noisy raise several questions. Why are quantum systems noisy? What is the nature and magnitude of the noise? Can we reduce via engineering the noise and make it negligible? Isn't noise and pure evolutions just a subjective matter? These and other arguments led several researchers to regard noise, even before quantum error correction and certainly after, as an engineering issue which has no roots in fundamental physics. The theory of quantum error correction and fault-tolerant quantum computation, FTQC, and in particular the threshold theorem, which asserts that under certain conditions fault-tolerant quantum computation is possible, provides strong support for the possibility of building quantum computers. Fault-tolerant quantum computing allows to embed via quantum error correction a noiseless universal quantum computer inside a noisy quantum computer. The overhead in time and space are rather small. So what we have is we have a huge Hilbert space which corresponds to the qubits, the physical qubits of our computers. And the actual behavior of the actual evolution of this huge Hilbert space is not a unitary evolution, but it's a noisy evolution that mathematically it can be modeled by a unitary evolution on these qubits and some additional qubits which we have no control of. Sometimes they are referred to as the environment of the computer. In any case, if we restrict ourselves to this physical qubit, the quantum fault tolerance allows us in this Hilbert space to find a logical Hilbert space, perhaps a dynamical logical Hilbert space, on which we have a perfectly noiseless unitary evolution. And we can simulate any noiseless evolution inside a larger noisy computer, and we don't even need a large overhead. So this is the idea. And there is one clarification which is important. In this lecture, noiseless means noiseless for all practical purposes. So the noise is extremely small. It can be exponentially small, but it's not zero. Once we have noise, we cannot move it all the way to zero. But if the noise is exponentially small, we will not encounter any errors in the lifetime of the universe. Then this is good enough for us. So the probability for errors is negligible. The quantum fault tolerance barrier. Quantum fault tolerance represents a major phase transition for noisy quantum systems. The main purpose of my work is to draw formally and generally the quantum fault tolerance barrier between noisy quantum systems with quantum fault tolerance and noisy quantum systems between noisy quantum system without quantum fault tolerance and noisy quantum systems with quantum fault tolerance. You know, once I'll come back to that. Once a calculus teacher in Jerusalem came to class and said, "Students, last week we talked about upper bound, and today we will talk about upper bound." So we know the students were, and then he called himself, said, No. Last week we talked about lower bound, and this week we will talk about lower bound." So the students start giggling. And then he caught himself, said, oh, I'm so confused. First I say twice lower bound, and then I say twice lower bound. And then they start laughing. So, okay, so we want to formally distinguish between quantum systems with quantum fault tolerance and quantum systems without quantum fault tolerance. And I think that this distinction, this formal distinction, is a major phase transition, even if quantum fault tolerance is possible. So if quantum fault tolerance is impossible, then this is a mathematical distinction between two types of systems, that one of them belong to the fantasy world, but still a very interesting fantasy world. But even if quantum fault tolerance can be realized, this represents a very major different behavior of physical systems that was to be studied. So here is a picture, a very schematic picture of the quantum fault tolerance barrier. So here, so to point here, it's not a good idea, but here we see the quantum systems without quantum fault tolerance are represented by the yellow region, and with quantum fault tolerance by this pink region. And this, of course, this map is out of scale, but it is sort of a schematic map that we will take with us further. Okay, the trivial flow. Now I come to some very basic flow in the thinking of many researchers in the area, which I refer to as the trivial flow. The term trivial flow, I think, was coined by Scott Aronson. So ignoring the possibility that quantum evolutions, whether they are human-made or natural alike, require special purpose devices whose physical properties depend systematically on the evolution they perform. So for general purpose quantum devices, the possibility for quantum fault tolerance reduces essentially to a single parameter. And modeling general purpose devices is much too narrow to deal with the issue of scalability. And what is ignored is that it is, in order to deal at all with the question if quantum computers can be scaled, you need to study the larger class of special purpose devices. This flow does not mean that quantum computers cannot be built, but only that many arguments and intuition for why quantum computers can be built are incorrect. It also means that this possible dependence between the evolution for all special purpose devices and the noise should be studied carefully. So here is a schematic picture of the situation regarding this trivial flow. So the large area represents special purpose quantum devices. And so this is a little bit confusing. General purpose quantum devices are much more restricted type of quantum devices, largely hypothetical, inside the much larger world of special purpose quantum devices. And here in this picture, this little ellipse represent general purpose quantum devices, which are largely do not exist. Now, if we want to understand if quantum fault tolerance is possible just for this little ellipse down there, then essentially this reduced to one parameter, which is the rate of noise. Essentially, if you measure the rate of noise using the right measurement, this is essentially only one parameter, which means that once you reduce the level of noise for the building block of the computer, then you can put them together and build as large computers as you want. Now, this intuition already is based on the assumption that you are in the general purpose device world. And my argument is that in order to understand what is the behavior of general purpose devices, we must enlarge the situation and study special purpose devices, and it is possible that the dependence of the noise on the evolution for special purpose devices, when we translate it back to general purpose device, means that we cannot cross the quantum fault tolerance barrier. So this is what was mainly ignored, and we will see various examples to that effect. So the trivial flow frequently asks questions. Does the connection between the evolution and the noise in violation of quantum mechanical linearity or other basic physical principles? The answer is no. Question: but current noise models do account for some relations between the noise and the evolution. And the answer to this is correct. They account for that in a very limited way, which is based on the general purpose quantum device description. So they account for that, but only in the gate noise and the specific description, or some more general but very specific description, which is all based on the fact that we have a single device which can compute arbitrary evolutions at will. Do you claim that each device can perform only a single evolution? No. The systematic relation between evolution and errors through a device should apply to all available evolutions for the device. The trivial flow frequently asked questions continued. But we could still build special purpose devices to factor large integers. Okay, so maybe you'll convince us there's no general purpose device, but we'll build a special purpose device and factor a very large number. No. We need to study special purpose quantum systems in order to understand if quantum fault tolerance is possible. If quantum fault tolerance cannot be realized, also special purpose quantum systems will not achieve computational speedup. Question: but qubits and quantum gates are not imaginary. Their quality is steadily improved. several plans for putting them together, for having universal quantum computers or highly stable qubits based on quantum error correction are on their way. And the answer is yes, some daring experimental attempts planned for the next few years will already challenge my conjectures. There are some experiments to build, there are some attempts to build very robust qubits based on quantum error correction, which, if they will be successful, will smash my conjecture to pieces. And then if my conjectures are correct, then these attempts will not be successful. And of course, it's possible that both these attempts will fail and my conjecture are also either incorrect or unuseful. I will come back to the matter of experimentation towards the end. I should say that one thing I kept reminding the reader in my debate in Aram is that even when Aram, in the rare case when Aram and I agree, it is quite possible that we are both wrong. And also in the cases that we disagree, it is also quite possible that we are both wrong. So you have to... Okay, so here is the quantum fault tolerance barrier drawn on David DiVincenzo's 7-stage roadmap to quantum computers. So this is a very nice picture of some steps that or a roadmap that was drawn by DiVincenzo in 2000. And this is taken from a recent paper of Devoré and Shelkoff from Science 2013. And you see that achieving logical qubits which are substantially more stable than the raw qubits they represent, so that we can operate or manipulate them, this is precisely something, this is where I draw the quantum fault tolerance barrier, and this is precisely what I think we will not be able to achieve. Or in any case, this is a very interesting mathematical distinction which describe this fault tolerance barrier. My conjectures. My first post in the debate with Aram Hauer described my conjectures regarding how noisy quantum computers really behave. These conjectures attempt to describe formally the quantum fault tolerance barrier. Some of them describe the simplest distinctions between my modeling and the standard noise models, and others in the standard ones for 1 and 2 qubits. Other conjectures apply to very general quantum systems. Note that these are not pure mathematical conjectures, but conjectures about the appropriate mathematical modeling of noisy quantum systems. We already talked about the trivial flow, and the trivial flow, I think it's an important observation which allow a much more general modeling of noisy quantum systems when we move to the realm of special purpose devices and don't concentrate it in the very restrictive area of general purpose devices. But several people raised the point, Elchanan Mosel and James Lee among them, that this trivial flow is very general. It amounts almost to saying that for some reason quantum computers will not work. And indeed, you need a very specific and detailed modeling to make the mathematical distinctions which describe the quantum fault tolerance barrier and which will not allow general purpose devices. So my first conjecture, no quantum error correcting for single qubits. This is a conjecture about the behavior of a single dynamical qubit. The conjecture reads as follows. In every implementation of quantum error correcting codes with one encoded qubit, the probability of not getting the intended qubit is at least some delta greater than 0, independently of the number of qubits used for encoding. Ordinary models assume the existence of some small delta for the individual qubit errors and reduces the amount of noise for the encoded qubit exponentially via quantum fault tolerance. So this conjecture go directly after one of the most important consequences of quantum fault tolerance. Note that this conjecture does not present a distinction on the level of physical qubits, on the level of raw qubits. For the physical qubits of the computer, this conjecture coincides with what the standard models assume. But it goes after a very important conclusion of quantum fault tolerance. Let me move to the third conjecture, which is about the behavior of two qubits. A noisy quantum computer is subject to error with the property that information leaks for two substantially entangled qubits have a substantial positive correlation. Now, this conjecture already poses describe a difference on the level of the physical and raw qubits of the system. I should mention, for those of you who don't know, that entanglement is the concept for quantum correlation. And it is regarded as a crucial computational resources and a crucial reason for why quantum computers have a superior computational power. And now this conjecture says that when we create entanglement, then the noise, the errors, or more specifically the information leaks for two entangled qubits must be must be positively correlated. And this conjecture is not in contradiction with the standard description of noise when the entanglement is achieved directly via gates. So if we have entangled gated qubits, then this description, while somewhat more specific, is in agreement with the standard models of noise. But what is different here is that the standard models of noise allows to cancel this positive correlation by using a quantum fault tolerance when the entanglement is achieved in an indirect way. And this conjecture is that this cannot be achieved. In any way you create entanglement between two qubits, in any physical device, then this entanglement is accompanied by positive correlation of the noise, or specifically of the information leaks. Conjecture 4, of a similar spirit to the previous conjecture, asserts that in any noisy quantum computer in a highly entangled state, there will be a strong effect of error synchronization. So error synchronization refers to the situation where we have perhaps a small probability of error attacking each of the individual qubits, but there is still substantial possibility that a large fraction of all qubits will be affected by the noise. So we have several phenomena of spontaneous synchronization in natural systems, and the conjecture says that no matter in every quantum device, when we create highly entangled states, on any quantum computer, noisy quantum computer, when we create a highly entangled state, then we will have this effect of error synchronization. So the conjectures that I describe are not pure mathematical conjectures, but they are described in mathematical terms. For the sake of this lecture, the most convenient way to describe them is still in natural language, in English in this case, but it is still useful to mention what are the difficulties and how you really put these conjectures on purely formal terms. So I found that the best way to express error synchronization, which is conjecture 4, and positive correlation for information leaks, which is conjecture 3, is by expansion to product of Pauli operators. So this is a base-dependent description. And then one result is that the conjecture about the behavior of pairs of qubits, when it's somewhat strengthened or slightly strengthened, is sufficient to imply the conjecture about error synchronization. And so the theorem is that conjecture 4 follows from a strong form of conjecture 3. In this strong form of conjecture 3, we need to replace the word entanglement by a measure of expected entanglement based on separably measuring the other qubits in an arbitrary way. So this emergent, so we have to for every 2 qubits, we have to talk about some emergent entanglement, which is described in terms of measuring the other qubits. And if you assume conjecture the 2 qubits behavior for this stronger notion of emergent entanglement, then you can deduce the error synchronization. So let me mention now 3 other conjectures. The first one is the Shor separator. This is a term suggested by Scott Aronson, and the conjecture says that the only realistic, approximately pure quantum evolutions are approximately bounded depths. And largely, this conjecture goes already to Unruh. Now, the idea here, Scott's idea was that a challenge was to describe what kind of states we will not be able to achieve with a noisy quantum a computer. And the answer is very simple. The answer says that we cannot achieve any outcome of more than a bounded depths computation. Of course, even in bounded depths computation, we will have severe restrictions, but this is already a serious separator. And in some sense, it tells us that the quantum computing, realistic quantum computation, is a heaven for computational complexity people, because in computational complexity, we can say definite, interesting thing about bounded depths computation, but beyond bounded depths computation, essentially, we cannot say anything definite. Here is the second conjecture, and this conjecture is something that I will zoom in the next part of the lecture. And the conjecture says that detrimental or damaging noise that cannot be avoided and cause quantum fault tolerance to fail can be described in terms of smooth Lindblad evolutions. I will come to that in a minute. And here is another conjecture. In any noise model, we have to say something about the rate of noise. And the description in the ordinary models of noise for quantum fault tolerance assume a fixed but small rate of noise for every computer cycle. And if you consider more general frameworks and you want less ad hoc description, so you need to pay attention to this matter, and the conjecture reads as follows: the rate of noise at time interval st is bounded below by a non-commutativity measure for projections in the algebra spanned by the unitaries expressing the evolution in the time interval st. So the noise, the rate of noise, is lower bound by a certain measure of non-commutativity. Okay, so this is about the conjecture. I want to mention one more thing about the conjectures about positive correlation. If you remember from the beginning of the lecture, my explanation for why quantum computers will not work assert that the rate of noise will scale up with the complexity, with the number of qubits and the complexity of the systems. So what is the relation between, why do I express the conjectures in terms of correlation when the major effect will be that the rate goes up? And here there is an interesting connection that I want to point out, and it is the following, that when we consider quantum fault tolerance, the relevant rate of noise is described in terms of qubit errors. And now what happens is that now it is natural to measure rate of noise in terms of trace distance. And this is the invariant parameter. And it turns out that when we have highly correlated system, then the rate of noise in terms of qubit errors scale up linearly compared to the rate of noise in terms of trace distance. So large correlation, high correlation will be quite damaging on their own for quantum fault tolerance. But the main damage they inflict is that they comes along with increased error rate. Okay, so let's go on with part 4, how to model quantum systems without quantum fault tolerance, or when error accumulation is not suppressed by quantum fault tolerance. So the mathematical tool I propose, this is a class of evolution which are called smooth Lindblad evolution. We start with a unitary evolution at time interval 0, 1. UST is a unitary operator describing the change from time s to time t. Next, we consider a general Lindblad evolution obtained by adding noise expressed infinitesimally at time t by ET. We replace ET by the weighted average of UST times ES times UST to the minus 1. So we conjugate ET by the action of the unitary, by the action induced by the unitary operator from times s to time t over all times s with respect to a positive kernel kt minus s. And we can just assume that the kernel k is Gaussian, where the time window is proportional to the evolution time. So we have this evolution time, we introduce this Gaussian kernel with certain window, and we apply this smoothing operation. So we start with a general Lindblad evolution where the infinitesimal noise is described by ET, and we move to a special type of Lindblad evolution where we apply this smoothing. So this is the mathematical object I propose. It can be applied to more general noise rather than Lindblad evolutions. Lindblad evolutions are form of quantum noise which are Markovian, so the environment does not have memory. But we can apply to more general, and we can also apply this idea, perhaps even more conveniently, in discrete time setting. In discrete time setting, we can talk about a very general situation where we have the unitary operation from time t to time t plus 1, and the error operation, which describe the effect of the error in this unit of time. Now, let me move as an aside an important point, which is that the kernel k of x is positive on the entire time interval from -1 and 1. And we average over all s in the interval 0, 1, both smaller and larger than t. And the reason we have to do it is because of, the reason to do it is related to some work I had with Greg Kuperberg. So the work with Kuperberg, whose title that Greg gave it is Preventing Quantum Computation Requires Time Travel, or something like that. And it says that if a consequence of our result, our result is described in more general terms, but the consequence of our result is that if the smoothing kernel k of x is 0 on the interval -1, 0, And in other words, if the smoothing depends only on the past, then fault-tolerant quantum computation is possible. So another way to say it, if we assume this, if we start with the standard model of noise, apply this smoothing only from the past, and apply the noise and describe it only in terms of the raw qubits, the physical qubit of the system, we can still achieve fault-tolerant quantum computation. And the way we do it is we use several ideas and results by Immanuel Knill and other people, and it relies quite heavily on fault tolerance using teleportation. Now, Greg's interpretation is described in the title of the slide, which goes after the title of the draft that he wrote, that he prepared, and Greg's mistake is the trivial flow, as Greg takes for granted the causality structure of general purpose devices. Now, the causality structure is much different for special purpose devices, and we will come back to that, but this is why this interpretation is incorrect. So let me just draw schematically the class of noisy evolution that we describe. Lindblad evolutions are fairly general class of noisy quantum evolutions, which are quite sufficient for many purposes, and certainly for the purpose of dealing with noisy quantum computation. And smooth Lindblad evolutions form a subclass of general. So smooth Lindblad evolution are a restricted subclass of the class of all Lindblad evolution. So here are two questions that people raised. So the first question was raised by Lukas Weck. This was a few days before I gave a lecture at MIT, and Lukas looked at the paper and he asked me, how can I say that these smooth Lindblad evolutions are subclass of all Lindblad evolutions when they have memory? So, as I said, without getting into any detail, the Lindblad evolutions describe a physical situation where the noise which represent the interaction between the system and the neighborhood, where the neighborhood has no memory. And now I claim that smooth Lindblad evolution is a subclass of the class of all Lindblad evolution, but it looks from the description that my evolution do have memory. So this is a nice point, because this is it's largely a mathematical point. How can my claim that this is class of this class of evolution is a subclass, which is a mathematical claim, it's not a conceptual claim, how it's coexist with our interpretation of Lindblad Lindblad evolution as memoryless, and with the fact that we do witness some sort of memory here. And another question is, isn't smoothing into the future violating causality? So is this smoothing, this mathematical operation that we make smooth, we take averaging, also with taking into account the future evolution, doesn't it violate causality? And those are very interesting questions, and the answer is no, that there is no memory, and indeed my noisy systems are subclasses of the class of all Lindblad noisy systems, and there is no causality violation. And we have to remember the trivial flow. The evolution and the consequence on errors are wired in the device. So we are talking about special purpose devices. The evolution is not a variable. The evolution is now a constant, and the evolution is wired in the device, and so are the consequences on noise or on errors derived from this evolution. So this is a very important point, and again, this manifests the trivial flow. And another question that was raised is maybe we can just change our mind in the middle of the evolution and make another evolution. And again, we cannot change our mind. In the ordinary experimental settings, we don't have the complete freedom to change our mind. I mean, changing our mind also borrow intuitions from the very restricted setting of special purpose devices, of general purpose or universal devices. In ordinary experimental setting, you just prepare the entire experiment, which is based on the entire evolution. You don't have this flexibility. So the Smooth-Limland evolution conjecture says that in every realistic noisy quantum system includes a noise component well correlated with the Smooth-Limland evolution. And I should mention that this description, this type of the conjecture, we move to the entirely opposite direction compared to the 1 qubit and 2 qubit conjecture. We now talk about very general quantum systems. These quantum systems don't even have a tensor, the Hilbert spaces. We don't even assume a tensor power structure on the Hilbert spaces. So we deal with very general settings. So the conjecture says that in every realistic noisy quantum system, we have a noise component well correlated with Smooth-Limland evolution. And the correlation description of smooth component of noise would say that the noise Et at time t or around time t has significant correlation with this UST times ES times UST transpose. And this conjecture applies to noisy quantum systems where the noisy state is close to pure along the evolution. And this condition also determines a natural time scale for the smoothing. Now, it is true that when we want to deal with setting of a quantum fault tolerance, we have to go away from the situation where the state is close to pure, and we also have to allow controlled evolutions which have also a classical part, which have also classical part which allows the classical control. And then the way to go about it is to represent this mixed evolution, mixed control evolution inside as a larger unitary evolution. But this is something which is left to be done. But so far, the Smooth-Limland evolution give you a description of realistic, or what I regard as realistic, noisy perturbation of a unitary evolution. Now, better approximations can be based on smoothing with respect to an internal clock of the evolution, which in turn is based on a measure of non-commutativity for the unitaries in the time interval. So, where in the description before, I more or less assumed that the clock of the evolution is consistent with the clock around us. And this is correct for noisy quantum computers if we consider the discrete time model. And but it may be that there is a better clock for the evolution, which is more appropriate for the smoothing. And this will give us a better approximation and perhaps better conceptual understanding. So I would suggest to make the smoothing with respect to a clock that, in accordance to the conjecture about rate, it depends on some non-commutativity measure for the unitaries in every time interval. In rough terms, a noisy quantum system is expected to have noise of two kinds. The first reflects the structure, symmetries, and clock of the ambient space, of the ambient device, the world around us. And this first kind of noise is quite similar to the standard noise for noisy quantum computers. And the second reflects the structure, symmetries, and clock of the internal process. So this type of dichotomy is something which I expect to occur in any noisy quantum system. And maybe I'll mention one example where we witness something of this nature, although it may have other explanation, and this is in Bose-Einstein states, and in Bose-Einstein states, which is a great triumph for quantum physics, some states which were predicted in the 30s were eventually created after many decades. And there we have many atoms, and the state of every atom is the same. So roughly the state, or I mean, ideally the state of every atom is the same. So we aligned all the atoms in a similar state. And when we talk about noisy Bose or noisy non-ideal Bose-Einstein states, then we can have two types of errors or fluctuation. One is that there is some independent noise acting on each atom. And the other is that there is a mixture of our single Bose-Einstein states with a cloud of different Bose-Einstein states. And indeed, both this type of noise are witnessed in reality, and we cannot get rid of any of them. And my proposed noise for general quantum systems is similar to the second one that I described, a mixture of different Bose-Einstein states. And this is also in according, in a slightly more general setting, with the first conjecture about how noisy decoded qubits look like. So this was an aside. Okay, so an important question is, what is the physical reason for my conjectured behavior of quantum noise, in particular for the smooth Lindblad evolution conjecture? And here I would like to say that the model of quantum computing is a huge abstraction, putting together under the same roof, under the same umbrella, many different systems. And the conjectured behavior also represents a major abstraction, and the specific physical reasons for it may depend on the implementation and may be studied very carefully on a case-by-case, via a case-by-case analysis. And there is another thing to say, that in addition, note that the main effect of the conjecture is to drastically limit the class of robust realistic quantum evolutions. For the surviving evolutions, standard modeling of noise can be quite close to the smooth modeling. So essentially, this type of modeling will require case-by-case explanation. So this is a universal properties of many systems which require specific explanation for individual systems, and it also has the strong effect of excluding away a lot of hypothetical evolutions. And for those left, the standard modeling is quite adequate.
We came to the end of the first video of our presentation. Let me end by bringing a comment by Dorit Aharonov. Dorit: it is true that in principle there can be a dependence between the computation and the noise. I always agreed with this point. But what is unclear to me is what type of computation the system should perform in order to generate such a dependence that will destroy the quantum computation. It always looked to me that in your explanations, the computation required to generate the noise is by itself terribly complicated. It is not reasonable to assume that every such dependence and every form of computation generating the noise is possible. So what should be the restrictions on the dependence you propose? In my opinion, the dependence should be simple in some sense. The dependence you offer, whose definition requires the system to actually compute its long-term past and future, does not look simple at all. This is what I refer to as unphysical. This is the crux of the matter. The perception that the system actually computes its long-term past and future is based on a causality structure of general-purpose devices. Dorit's claim does not apply for systems based on special-purpose devices. In such systems, the past and future of the evolution are wired in the device, and the system does not need to compute anything in order to generate the noise. Without the flawed intuition regarding the computation required by the system to destroy the quantum computing, my proposal is actually quite simple. Here is an example. Consider the following claim. In a manned mission to the moon, the risks near takeoff are larger when we land on the moon compared to a mission when we just circle the moon. This higher risk does not mean that the failure mechanism is based on some terribly complicated computation of the future, but rather simply that the equipment required for landing on the moon makes higher risk near takeoff.